giving me the chance to be a moderator today. We are satisfied to inform you that our speaker today is Dr. Wilson Wong Pun Chiong from the University of Malaysia. Sorry if I have misread your name. That's all. He is assigned as the head of program of Nature Park and Recreation, the Faculty of Tropical Forestry of the University of Malaysia Sabah. And he has graduated from Diploma of Science at the University of Malaysia in 2002. Chair of Forestry Science at the University of Malaysia Sabah in 2005. And Master Program at the University of Malaysia Sabah in 2011. And he has graduated from the doctoral program at the University of Tokyo, Japan, especially in Graduate School of Agriculture and Life Science. Actually, he was my tutor when I took doctoral program in 2018. Good morning, Dr. Wilson. Nice to meet you again. How are you today?
Okay, thank you. Good morning.
Okay. Thank you for accepting us to be one of the international speakers in online summer course this year. Okay, ladies and gentlemen, before the presentation starts, let me tell you how the course will go. First, Dr. Wilson will be invited to present his topic on application of remote sensing technology in forestry for approximately 40 to 45 minutes, and then after that we have a question and answer session will be conducted, and the participant can write down the question in the chat room or click the right hand button in your application before I allow you to open your microphone to ask the question. Without further ado, let's start the course. I would like to welcome our speaker to start this presentation. Dr. Wilson, would you just send your presentation by yourself?
Okay, thank you, Dr. Kiswanto, for the nice introductions. And good morning to all the organizing committee and participants for this online summer school course. So it's a great pleasure to meet online with Kiswanto after I think 6 years from when I left Tokyo in 2016. Okay, I think there's a call just now. Okay, so it's good to be invited in your summer school organized by the Universitas. Okay, so maybe did you get the echo just now? No. Okay. Okay, so I will start. I try to be on time. Only 45 minutes. According to the time allocated. On applications of remote sensing forestry. So I think it's very challenging to deliver this topic in 45 minutes. Usually, we have a series of lectures, okay, to give an understanding about this remote sensing technology, because there are so many technical things, and I hope at least at the end of this talk, so the participant can get some ideas how to use remote sensing technology in forestry. Okay, so I think I've been introduced by Dr. Kiswanto just now. So I graduated from University of Tokyo 2016. So my research interests basically on spatial valuations of ecosystem services. So, and also remote sensing. So my specializations, especially on aerophotogrammetry. Okay, so I did several courses like biometrics, environmental service evaluation, storage economics, and also environmental land use planning. Okay, so just basically show the locations of my current locations. So about maybe 1,000 kilometers from Universitas Mulawarman. So by walk, maybe I need to walk 250 hours to get there. Okay. And yeah, so actually we are close, but there's no direct flight to Universitas Mulawarman. So hopefully in future we have a direct flight, because I think soon the capital of Indonesia will move to Kalimantan, right? Okay. Okay, so coming back to the business, so I will talk about the background of remote sensing to give you the participants ideas about the remote sensing technology, the sensors. So I will give an overview of the sensors available and how to get the remote sensing data. Okay, they are free data set. They are paid and they are especially for higher resolution. And I will talk about the technical aspect, brief about the technical aspect of the resolutions of remote sensing. This is very important when before we decide to use the remote sensing data set. Okay, so we'll talk about that, and I will show one simple example, brief examples, how we can use in forestry. So in my case, I will show examples how we use the LiDAR data, aerial photograph, estimate above ground biomass. Okay, in tropical mountain forest. So is my sound clear in the slide? Is my sound clear in the slide? Dr. Kiswanto? Is it clear?
Your sound I think is double.
Yeah.
It's double sound. I hear it.
Is there problem? Oh
no, it's okay.
There's a echo, right? So maybe I have to switch off my video. Is that okay?
Is that okay?
Yeah. Yeah. Okay, so I think, yeah, so sometimes we need to switch off the video, so maybe it will be more smooth. Okay, so often we deal with large area in forestry, and still, I think still probably audio. Do you? It's
Yeah,
okay, the video, the audio.
I hear double sounds.
Double echo. No, not sure what's the problem. Okay, may I continue?
Yeah, sure.
Okay, so I think something wrong with the internet connections. Okay, so often forest is a large area. For example, in Sabah, approximately 53% of the total land area is a forest reserve. Okay, so we deal with a large area. Okay, so if you want to do monitoring or assessment, for example, on biomass, so we need technology. Okay? In this case, the remote sensing technologies offers an opportunity for us to do assessment on large area, for example, on biomass estimations, and also maybe multi-temporal. So maybe we need to, for example, for biomass, we need to monitor the biomass every, for example, N years, for example, maybe 3 years or every 5 years. Okay, so using conventional inventory, so that it will be resource intensive. Okay, so remote sensing nowadays offer alternative to do such assessment. But however, so although we can use a different data set, so sometimes we need to consider technical issue. For example, using this evitable biomass map, so we can have a biomass map for the entire palm tropical. Okay, but the issue is you count when we need the biomass map for different purpose. For example, under RED Plus, you need high accuracy and robust assessment. Okay, so for example, in this case, you can see the same area, but on the left panel, okay, so the resource is 1 kilometer, but on the right panel here, the resource is 30 meters. This is from LiDAR dataset. Okay, so obviously from the LiDAR dataset, we can obtain more detailed biomass value. For example, you can see this area denoted by red colors. Okay, is a high biomass area, while the blue colors are low biomass area here. Okay, so we can see a very detailed, and even we can see this is the actually logging road. Okay, you can see the logging road here, and this is the paddy field by the farmers. Okay, so in certain cases we may need high resolutions remote sensing data set, like for example for RED Plus program. Okay, a little bit about background of remote sensing. So the term photogrammetry has been used since 1867. Okay, and the term remote sensing was introduced and it was officially used in 1962. So what is remote sensing? So this is the definition. So remote sensing is a science and to some extent art of acquiring information about Earth's surface without actually being in contact with it. So this is done by sensing and recording reflected or emitted energy and processing, analyzing and applying that information. Okay. So we have a different sensor types from a space sensors being mounted on spaceborne, for example, satellites, or also in some cases shuttle missions. For example, our popular SRTM data for digital elevation model. So it's come from a shuttle missions in 2000s. Okay. So, but most of the satellite data sets so comes from these satellites orbiting the Earth. Okay, so for example, STGDAM, ISAT, and TerraX. Okay, so we also have an Airborne platform. It's basically Airborne. The altitude is up to 6,000 meters, and the important also there are these different sensor types. We have imagery or photographs. Second one, we have the LiDAR data set. So I'll talk a little bit detail about LiDAR data set in the next several slides. And third data set, we have this SAR data. It's abbreviations for synthetic aperture radar. Okay, so basically a remote sensing data set can be categorized into 3 types. Okay, imagery, LiDAR, and SAR. So the advantages of satellite observations. Okay, so we can do a large spatial assessment. It could be cost-effective for certain applications. Number 2, multi-temporal assessment. Okay, we can up-to-date informations and change detection assessment. For example, biomass estimations under RED Plus, we need to estimate it for every 5 years. And then it can reveal invisible informations, okay, beyond the visible spectrum, beyond the wavelength that we can see, the human can see. Okay, so it can also reveal, for example, infrared informations, thermal information for various applications. Okay, so this includes detecting disease or forest health. Okay, and then next, it enables observations and retrieving informations in restricted and inaccessible area or without visiting the area. So often forest is a very large area. So often maybe it's almost impossible to every forest area in our maybe start area of interest. Okay, talking about the sensors, so I go a little bit details. Okay, and this is the number of operational satellite in 2016, 1,459. So just imagine the number. Anybody know what's the number of operational satellites now maybe in 2021? Anybody have ideas? Does it remain or it still it increased? Okay, so the answer is now we have in 2021 we have 4,852 satellites. Okay, so these compilations by UCS USA. Okay, there are lots of satellites there. Okay, so common types of satellites. I think you heard about the like communication satellites. Okay, space telescope. Okay, but in remote sensing, we use the Earth observation satellites. So if you heard about Landsat, okay, so Landsat is one of the Earth observations satellites. We have navigation satellites. Okay, so we have the GPS system. We have the GLONASS owned by the Russia, and also recently we have the Galileo by European Space Agency. Okay, and also we have a weather satellites. Okay, so in 2016, so US on about 600 satellites. Russia about 100, and China also about nearly 200 satellites. But in 2021, so we can observe here the informations. US already increased the number of satellites significantly. Okay, so Russia still about 100 satellites. China's also increased to almost 500 satellites. Okay, so there are many satellites. So you can see this is 1966 only Russia and US and Canada have satellites. Currently, so almost all countries have their own satellites. Okay, and this is the orbit, the satellites orbiting the Earth. So basically, we can categorize into high Earth orbit. This is basically the weather satellite. Medium Earth orbit from 2,000 to 35,000 kilometers. So this is usually the navigation satellite, like the GPS. And then we have low Earth orbit. Okay, so just like our and also our ISS, International Space Stations, orbiting I think about 400 kilometers. Okay, Landsat is about maybe 700 kilometers in altitude. And most Earth observation satellites is on the low Earth orbit. Okay, for your information. Okay, so I will show you a video.
As a Landsat satellite flies over the surface of the Earth, the instruments aboard the satellite are able to view a swath 185 kilometers wide and collect images along that swath as the satellite proceeds through its orbit. The spacecraft travels at approximately 4.7 miles per second. The satellite travels from north to south while it's over the sunlit portion of the Earth and travels south to north over the dark side of the Earth. One orbit takes about 99 minutes. So that's about approximately 15 orbits in a 24-hour period. The orbit's maintained such that after 16 days, the entire surface of the Earth has come within view of the Landsat instruments while sunlit. And then on day 17, the first ground path is repeated, so we get to view the entire surface once every 16 days.
Okay, so I think everyone has a glimpse on how Landsat actually taking images. Okay, so this show the spacecraft system. So as you can see here, so we need the sensors. Okay, for example, Landsat have two sensors, which is called OLI, optical line imagers, and TIRS. Okay, TIRS is a thermal infrared sensor. Okay, so in overall we can get 11 bands from Landsat 8. Okay, so there are these complicated systems, including the radio system, so that the images can be transmitted to Earth, and user can download the data set after being processed, okay, by to different level product. For example, we have level 1, level 2 products. Okay, so there are lots of satellites out there, just for your information. Okay, so the popular one is Landsat. Okay, we have the EO. Okay, we have Primus. Okay, Aqua, ISAT. Now we have ISAT 2. ISAT 1 is already not or broken. Okay, not more in operations. For spaceborne SAR, we have also different satellites. Okay, by different owned by different country. Okay, for example, the popular one we have Allos-Palsat, owned by Japanese Space Agency. Okay, so now we have Allos-Palsat 2. Okay, so this is another showing the different SAR spaceborne SAR system. The most anticipating one of the most anticipating satellite is actually biomass. Okay, initially it was scheduled to be launched in 2019, because of maybe a delay. So it is rescheduled to be launched in 2023. Okay, according to the latest information. Okay. So SAR have this just show you different techniques for SAR processing. I will not go into details. Okay, so there are different way of processing, for example, SAR data from polarimetry to holographic tomography. And then we also have Airborne SAR, okay, with different bands. And next we have Airborne LiDAR. Okay, so this actually use the laser technology, okay, together with the GPS or GNSS, Global Navigation Satellite System, and Inertial Measurement Unit, IMU. And often the common data format is in LAS format. Okay, this is point cloud. Okay, so for example, in a small area like 2,000 hectares, we can deal with maybe up to 800 million point clouds. So very dense. Okay, but again, it depends on the setting, the parameter settings. So we can have reduced point clouds or very dense point clouds. Okay, so this example of LiDAR, you see this from the laser. So we can get the 3D informations. Okay, so this in point, we call it in LAS format or in point cloud format. Okay, so basically the LiDAR system will we will scan it, and we often get different returns. Okay, from the first return, second return, third return, up to last returns. Okay, so it did also depending on different vendors. So you can get seven returns. Okay. Okay. Again, there's a development in aerophotograph or photogrammetry. Okay. So the development of image matching algorithm, especially in established in computer vision field, so make a new opportunity to use aerophotograph for various applications, including in forestry field. Okay, so again, for aerophotograph, you can have a different format. Okay, from large formats, very expensive, can be several $100,000 or maybe just a small cheap camera, maybe $1,000. Okay, so each aerophotograph formats will deliver different quality. Okay, so we'll talk about that one in the next subtopic outline. So basically, we have this flight line. Okay, and they must to optimize the the image matching. So we need overlap, photo overlap. So we have forward overlap and side lap. Okay. So often forward overlap now we set as up to 80% forward overlap and side lap up to 50%. The previous photogrammetry approach, so they only set 20 or 30% side lap. Okay. So in the previous technology, but using the image matching algorithm, we need higher number of overlap. And then for the platform, you can put the camera or the sensor in small aircraft, for example, or helicopter. Okay. So this can be effective for national or subnational data acquisitions. Or sometimes we can put the camera in this drone, or often called UAV, unmanned aerial vehicle. Okay, so we basically we can have this fixed wing drone or multi-rotor drone. Okay, so this technology UAV can increase capability and reduce cost, especially for a small area. Okay, so the price range from $100. Even the drone can be tens of $1,000s, especially if it comes with RTK GPS. Okay, so when it comes with RTK GPS, that means your position, the camera, the aerial photograph camera is more accurate compared to cheaper UAV drone, okay, without the RTK GPS. But of course, there's a solution. You can put a ground control point or target. Right? Often, maybe we will set maybe 10 ground target, okay, to improve the accuracy using low-cost UAV. Okay, so of course, usually in the market they have only this single RGB, but now we have even a multi-spectral camera. Okay, like MAPIR sensor. If you work with UAV, you may come to heard about MAPIR or Parat Sequa. Okay, also provide a multi-spectral camera you can attach to the UAV. Okay, if you have questions, you can raise up your hands. Okay, so maybe we can have an interactive discussions. Or you can keep the questions to the end of the sessions also. Okay, I will continue. So how to get the RS data? Actually, many of the remote sensing data you can get for free. Okay, especially lower resolutions images like Landsat or Sentinel. For example, you can go to this Earth Explorer. Okay, and just maybe sign up for the first time, and then you can look at different data set here. For example, even aero imagery, especially in US, you can get some aero imagery in that locations. Okay, but if you are working in your area in, for example, Southeast Asia, so often you can easily get the Landsat dataset or the Sentinel. Okay, even the digital elevations from SRTF, you can also download it from here. Okay, so part of that, the Earth Explorer, you can also use, for example, the Clovis. Okay, so this is also supported by USGS. Okay, so you can also use this platform to download. So there are at least 2 different ways to download the Landsat data. Okay, so for example, if you want to work in Samarinda, okay, so at least now there are 660 scenes for these 3 areas. Okay, and Landsat size is about 180 kilometer by 180 kilometer. Okay, and it's free now, but before 2008, we need to pay for the Landsat. So I think at one point, they sell up to maybe $3,000 or $4,000 for one scene, And after that, I think in 1990s when they launched the ETN Plus through the Landsat 7. So they sell, I think, around $600. Still expensive. Okay, $600 for one scene. So often, sometimes we use more than one scene. For example, to cover all Kalimantan, I think you need maybe 20 scenes. For Sabah alone, we need at least 8 scenes to cover the whole area. Okay, and often you can see if we have problem with the cloud. So this, I think, Kiswanto now won't have a deal with this cloud issue. in his research. Okay, for Sentinel, you can get Sentinel dataset from the Copernicus Open Access Hub. Okay, so it's the Sentinel owned by the European Space Agency. So Sentinel-1 is the SAR dataset. Okay, Sentinel-2 is the optical imagery. Equivalent to Landsat dataset. Okay, so I think it has, if I'm not mistaken, it has maybe 10 beds. Okay, for Sentinel-2. Okay, so for high resolution, so often this, for example, Sentinel-2, it has a 20-meter resolutions. Landsat has a 30-meter resolutions, and you can get higher resolutions. For example, from Iconos or QuickBird up to 0.6 meter, very detailed. Meaning to say, we can detect maybe house or vehicles. But using Landsat, you can see the resolution is often 30 meter, so we cannot see very detailed objects. For example, detect car, individual tree. But using very high resolutions image like Iconos or QuickBird, we can detect the crown, the forest, the canopy crown. So in some study, you may want to use very high resolution images, for example, from QuickBird or even GeoEye. Okay, and often these images it's not free. You need to buy it. Okay, so there's a cost. For it. There's a minimum order area. You cannot order just maybe 1 hectare. Okay, so in this case, you need 100 square kilometer, equivalent to, I think, 10,000 hectares. Okay, equivalent to 10,000 hectares. Okay, so this is the price. Okay, so yeah, so you can get more if you interested. Some of the images you can check. They have a minimum order and the price. Okay, price also different. There are different price. So if it's archive long, maybe previous years, so it's cheaper. But if it's new collections, often it will be the price is a little bit higher. Okay, for example, for GeoEye, if new images, it's $20 per square kilometer. So 1 square kilometer equivalent to 100 hectares. Okay, so $20 for 100 hectares. Okay, so that is for satellite dataset. Airborne dataset usually if we have a project, we can hire vendors to provide, for example, LiDAR data or aerophotograph. For example, in our case, in 2011, we flew the LiDAR sensor. This is actually the LiDAR sensor here. And this is the camera. So we use the DSLR camera. Okay. So we took 2 different data sets. And of course, it comes with the GPS. I think the GPS, maybe they put it somewhere here. Okay. So yeah. And then we need, of course, beside the maybe a cost, we need also permissions of relevant government agency. For example, in Sabah, to fly drone, and we need at least permission from 3 government agencies, namely the Chief Minister Office, Civil Aviation Agency, and the third one is from Land and Survey Agency. Okay? So we need to comply with the laws. For example, now we have a law regulating the use of drone. Okay, for any purpose. We have this law established in 2016, quite recently also. Okay. So you may check if you want to use drone. You may need to check the regulations in your own country. Okay. Okay. So I will move to the next one. I think this is important. We need to understand the resolutions of remote sensing. Okay, especially for optical sensor. So it can be described as a spatial resolutions. Number 2, spectral resolutions. Number 3, radiometric resolutions. Number 4 is temporal resolutions. Okay, so remember these are 4 different resolutions. It's important. The first one is spatial resolutions. As you can see, on this one left is satellite image, the Iconos. Okay, the Iconos image, 1 meter. Okay, and on the right panel here, this is a arrow image, 10 centimeter resolutions. Okay, so obviously, by using higher resolutions, you can, for example, detect the canopy. For example, if we are doing study related to maybe tree canopy identifications, so we may need to use aerophotograph in this case. And for the spaceborne imagery, it can count from 1 meter to up to 500 meters. For example, from the MODIS satellite. Okay, Landsat is 30 meter. Sentinel-2 is 20-meter resolutions. And next for the spectral resolutions. Okay. So spectral resolution describes the ability of a sensor to define fine wavelength of intervals. Okay. The number and width of spectral channels, more and finer spectral channels enable remote sensing of different parts of the atmosphere. Okay. So for example, Landsat, it has here you can see 11 bands, okay, covering different spectrum of the wavelength. Our eyes only can detect what we call the visible wavelength from basically from 400 to 700 nanometer of the wavelength. Beyond that, our eyes cannot see, but the instrument can see the lights, okay, and which is very useful in certain applications. For example, to assess maybe, for example, forest health, okay, or to use in biomass estimations. Okay, so with beyond the visible wavelength information, so that will be useful, okay, for many purposes. Next, we have radiometric resolutions. Okay. So it describes the ability to discriminate slight differences in energy. Okay. So the higher the radiometric, the better. Okay. So for example, in this case, you can see from the image provided, the top one, you only have 1 bit data. So only 2 divisions or 2 levels of brightness. But if you have higher radiometric resolutions up to, for example, 12-bit data, so you have 4096 levels of brightness. Okay. Okay. So next we have temporal resolutions. Okay. So temporal resolutions indicates the time increment of a data set or the frequency. Okay, the frequency or the interval at which data was measured. Okay, so for example, Landsat 8, it has 16 days temporal resolutions. Okay, so mean to say every 16 days the Landsat will for example Samarinda. Okay, Samarinda area. Okay, so it has the orbit. Just now from the video I show you. So it will return to its orbit after 16 days. Okay, for airborne remote sensing, so temporal resolution is determined by flight campaign. Okay, so not many countries have a national flight campaign. For example, even Japan, they don't have at least in 2016 they don't have a national flight campaign. It's based on project based. Okay, so maybe they want to scan certain area, they will fly. But in certain countries, for example, in Switzerland, they have a national aerial imagery campaign. So the temporal resolution is 6 years. Okay, so the next slide show this the flight campaign in Switzerland. Okay, you can see here different color, indicate different flight years. Okay. So for example, the yellow color, this red color, so it will scan 2007. The next one, it will scan 2013 lah. Okay, and it will repeat the cycle. And then the next one maybe if they don't change, so they will scan in 2019. Okay, and they have different resolutions also. You can see on the right diagram here. For mountain area, they use 50 centimeter or 0.5 meter GST. Okay, ground spatial distance ataupun or the spatial resolutions. For populated area, higher resolution, which is 25 centimeter. Okay. Okay. Any questions? So far, okay. Okay, you can keep also the questions to the end of the sessions. Okay, so applications of remote sensing in forestry. So we can use remote sensing dataset for many purposes. Okay, for example, I work mainly on biomass estimation. So we use different datasets, satellite images, LiDAR data, aerophotograph. Even now, I'm looking to explore the use of synthetic aperture radar dataset. Okay, so we can use it for example, leaf area index estimations, forest attribute estimations. For example, you can estimate the basal area, the dominant height, tree densities, okay, and so on. And also you can use it for land of forest cover classification. And those data can be further used, for example, for conservation status of species. Okay, so often for conservation status of species, we need to model the distributions of the species. Okay, and for many other uses. So for this purpose, I will show you just one example because of limited of time. So this is the slide I used to present in Asian Conference on Remote Sensing back in 2016 in Sri Lanka. Okay, the title is Above Ground Biomass Estimations using Airborne LiDAR, okay, or Airborne laser scanning and structures from motions. Okay, structures from motion is actually aerophotograph, okay, in tropical mountain forest. So the objective is to evaluate and compare Lgb estimated using the LiDAR data. This is the LiDAR data here, okay, and structures from oceans, meaning to say the aerophotograph data set. Okay, okay. So you can from these our observations, LiDAR point up to the forest floor. Okay, so you get a point from the tree canopy up to the forest floor. But the airphoto to only the level. Okay, because it is a passive system. It depends on the light. It detects actually the lights reflected, okay, from the sun energy reflected from the forest canopy. Okay, but laser it emits the energy, called an active system. Okay, so this is study area. So actually, just border with Kalimantan, the Kayang Mentarang National Park. Okay, so this is a highland area. Okay, so we deploy 45 plots for about 2,000 hectares. This is the area. Okay, so this area is the elevation is from 1,000 to almost 2,000 meters, and it's dominated by deep thoracic mountain oak, okay, and agatis species. The land use range from logging activity, shifting cultivations, and settlement. Okay, so this is the locations of plot. Okay, so we have 45 plots measured in 2011 to 2014. And we deploy 30 by 30 plot size. Okay, and we took the GPS informations. Okay, so often maybe sometimes when you heard remote sensing, so maybe some perceptions, we don't need the ground truth or go to the forest, but in fact we need to go to the forest, okay, to get the data, okay, the ground data. In this case, we took the GPS information using advanced GPS, the different, what we call it as a differential GPS, and we measure the tree with diameter more than okay, and we took the information of the diameter and also the tree height. Okay, so we measure the tree height and also took the diameter. Okay, so we measure, for example, in this case, we have, I think, almost 100 trees. Okay, and then we compute the informations, for example, the mean dB heads, the basal area, and tree density. So in this study, so the objective is where we look at the Lgb, okay. So this show the instrument used, the advanced GPS instrument or survey grade GPS. Okay, so this day also one equipped with GPS chipset where we can detect location using our smartphone. Okay, and I believe some of you also have used the Garmin handheld GPS. Often the accuracy is 2 or 3 meters or more. Okay, but using this survey grade GPS, we can get high accuracy up to 2 centimeters in open area. Okay, so very location is survey grade GPS. And often it's expensive. I think it will cost around, maybe if Java, maybe it can cost up to $10,000 US, if I'm not mistaken. Okay, it's quite expensive. Almost you can buy a car, I believe, $10,000 US. Okay, and recently we have also options. There's this Colida survey grade GNS receiver. Okay, so the price is something like, if I'm mistaken, like maybe 3,000 US dollar, maybe something like that, Okay, so much cheaper from other brand. And yeah, so we need this, maybe one of the challenge to go to the plot. Maybe sometimes we need to cross the river. Okay, and sometimes we need to hike. Okay, bringing our camping and set a camp so that we can collect maybe 10 plots in that area. Okay, so these often are very challenging especially in tropical. Okay, so of course after getting to the plot, so we will get the data, the scientific data, like maybe the tree height, the tree diameters, and in this case also we took soil sample to address certain other study objective. Okay, in our case, we focus on the Lgb estimation, so we compute the Lgb. In this case, we use the Yamakura functions. So from the survey, so we get the Lgb value 45 plots. So this information is used in the further analysis. Okay, but before that, we need the remote sensing data set. So the remote sensing data set count flight missions in. This is the LiDAR sensor. This is a Regal LiDAR sensor. Okay, this is the Canon camera. Okay, so this is the technical information. So the Regal LMS Q560, the LiDAR sensor, provide pulse density up to 15 pulses per square meter. So this is a relatively high density for LiDAR applications. But because of research purpose, so we propose the density up to 15 pulses per square meters. Okay. For the Aerophoto, this is the information. So we have the GSD, the spatial resolutions, 10 centimeter. And overall, for 2,000 hectares, we have 2,400 aero photograph. Okay. And then we process it. So I will show how we process it in the next slide. Okay. So basically, from the 2,400 aero photograph, okay, so we can create 3D informations, okay, or 3D point cloud. So there are four main steps. If we are only deal with the point cloud, the 3D information, so we only need two stages. Okay. So for example, processing 400 photograph. So took all together the first stage 4 hours using workstations. Okay, much higher computation capability. And for the stage 2, it took around 9 hours. Okay, in total, we need 13 hours to produce the point cloud for 2,000 hectares. Okay, so this shows the prospective profile of the points from aero photograph, denoted by the green color. You can see, okay, from here, basically the aero photograph can detect. The blue colors are the LiDAR data. You can see the LiDAR data because it emits the laser pulses, so it can detect from the upper corner. You can see the branches here, okay, even the trunk and even the forest floor. Okay, this is from the LiDAR. So you get a very detailed 3D information of the forest. And a part of that, you can also get orthophoto from the aero photograph. Okay, so in this case, we get a 25 centimeter orthophoto. So this is a technical thing. So often there are technical parts you need to deal with. Okay, so I will audit just to highlight that there are technical things to consider when you use remote sensing data set. Okay, often I think this is the major check. I think Dr. Kiswanto agree on it. So often we spend hours to process our data, our remote sensing data set. Okay. Okay, this again, the technical things. We derive many variables. In this case, we derive 25 variables. Okay, so of course we can derive more than these variables if, or even you can propose new variables. Okay, it can be a novelty in a remote sensing study. Okay, so this is the flow chart. So you have the LiDAR data set. You get the canopy echoes. Where you filter the 2 meter. You get the variable just now, 25 variables altogether. And then you do log transform. And in this case, for example, you use these multilinear regressions. Okay. Of course, for prediction method, there's another predictions method now popular called learning algorithm. Okay. For example, from random forest or support vector machine. Okay. So from the field data that we collected just now, the Lgb, okay, is being used to, for example, for modeling the edge. So together with the predictive variables from the remote sensing data set and the field data, so we can model Lgb. Okay, the Lgb is the response variables. And then of course we need to check the accuracy. Often we can do cross validations, for example, using LOOCV, leave one out cross validations, and we get the RMSE value. Okay, so this is the result. The result from LiDAR data and the aerophotograph, and you can see that the accuracy not so much different. Okay, almost as accurate as the LiDAR. So LiDAR is known to produce the best accuracy. And the R-square, for example, here is 0.79, but aerophotograph is not so far. It's 0.74. Okay, so it's almost similar. And the relative RMSE only different at 2.68%. Okay, so this is the result of the Lgb estimations from the modeling Lgb model. Okay, this the upper one from LiDAR, the lower one from photograph. Okay. Again, you need still to deal with the node. For example, in this case, no data area. Okay. So the aerophotograph in this case failed to produce the 3D information. Okay. Okay. So this is the technical issues lah. We can maybe do research. Okay, for example, you can try different camera or sensor, try different flight parameter settings, or overlap rate, for example. Okay. So I will just skip this one. This is additional discussions. So the main thing in this, for example, from our study in this is presented. Okay. So we show that you can use the aerophotograph for monitoring purpose. Once we have the detailed from LiDAR data, because LiDAR is still very expensive this day, but to fly aerophotograph, I think it's cheaper. You can use even drone. Okay, so for operational purposes, so there's a opportunity to use aerophotograph with combinations of one-time LiDAR data. Okay. Okay. I think I just maybe 50 minutes, almost 1 hour. Okay. I think I've tried to cover so many technical things within 1 hour. That's very challenging for myself actually. So I hope all the participants get some insight, okay, about remote sensing, how we can use. Okay, of course, those who in Universitas Mulawarman, you can maybe go to talk with Dr. Kiswanto. He also expert in remote sensing. Okay, also Dr. Ali, Dr. Rustam. Yeah. Okay, so thank you for listening. So if they have any questions, you can have maybe discussions.
Okay, thank you very much, Dr. Wilson, for providing us with the informative and incredible explanation about certification in forestry. Yeah. Actually, we have the end of time because this is 11 o'clock. But I can give you 5 or 10 minutes more for question and answer sessions. So if you have question, please feel free to click raise hand button in your application, and I will be allow you to activate your microphone to ask the question directly. Before that, I see in the participant list there are Pak Ali Suardiman. Pak Ali, are you there? You can say hello or just comment for the Wilson presentations. Pak Ali?
Hello, Bakis.
Yeah.
Hello, Pak Wilson. Wilson-san, how are you doing? Yeah, maybe I don't have a question, Bakis. Just say hello to Pak Wilson-san. I'm in the middle of the proposal seminar of our students, so I just monitor the presentation of Dr. Wilson. It's very good, very nice presentation for all of us, because we don't have type of mountain tropical forest, right, in East Kalimantan, and we only have tropical mountain forest in Sabah, in Malaysia. So I think the topic is very good. It open our understanding about the mountain forest in Borneo, same island with us in East Kalimantan. I think that's it, Pak. Yes. Thank you.
Okay, thank you, Pak. Thank you, Pak Ali.
Thank you, Pak Ali.
Yeah, maybe someday we will collaborate.
I think
to
questions from from Aulia.
Yeah.
Balkis. So
Yeah.
should I first the
you can answer this question.
Yeah. So the question is by Aulia. Balkis is which of all the remote sensing instruments are most common used in monitoring deforestation? Okay, so that's I think the first questions. The second question is, and a satellite is able to collect good quality images if they are ongoing wildlife smoke. Okay, so I will answer the first one. So the most common use in monitoring deforestation is the satellite imagery. Okay? Maybe from Landsat dataset or Sentinel dataset, and also even many studies also use the MODIS dataset with a higher or lower resolutions. Okay, so often we need to use this available satellite images to monitor deforestation, and in some cases also there's also study to explore the use of the SAR dataset, the spaceborne SAR. For example, like Tulsa dataset. Okay, so we can use those that remote sensing dataset to monitor deforestation. Okay, the second questions, are satellites able to collect good quality images if they are ongoing wildlife smoke? Okay, so the answer is depending on our objective. If you want to, for example, land cover classifications, okay, so this smoke or maybe cloud will be a problem for processing. Okay, so if you have, for example, haze, but is distributed evenly, you can maybe perform, for example, atmospheric corrections. Okay, atmospheric corrections. But if you have wildlife smoke, so maybe it's difficult to perform. Depends on if it's the smoke is very heavy. So I think it's a problem to process. is okay, the Aulia?
Yeah,
Okay.
I think, yeah, for the time series monitoring, maybe only Landsat and Sentinel, right, Wilson?
Also, maybe they use also MODIS.
Yeah,
You can use MODIS
yeah, for the time series, right?
Yeah. And sometimes they combine different data set that produce the result. Yeah.
Okay, thank you, Dr. Wilson. Is any questions? I still check in the list participant and or chat room. As there are no questions thus far, I will, maybe simple question for discussion, Wilson.
Yeah.
Regarding to the main topic of this course, tropical rainforest extinct. I would like to know your opinion about us as remote sensing experts. Do you agree that tropical rainforest will become extinct?
I will not totally agree on it. So I think, for example, now this day, many of the stakeholders, including the government, the NGO, the academic institutions, now pushing for the conservation aspect to protect or preserve a protected area. For example, in Sabah, 53% of the land is a forest reserve. Of course, some portion is a commercial forest reserve where logging activity are being permitted. But also, for example, in Sabah state, we are heading for 30% of the land is totally protected by 2025. Now we already achieve, I think, almost 27% of the 7 million hectare in Sabah. Out of 27% now is totally protected, meaning to say, no any activity, no logging activity, no shifting cultivations is totally protected. And I guess the international commitment also want pushing all countries to achieve 30% totally protected area by 2030. Let's call this 30 by 30 tagline. Okay, so of course there will be a challenge to achieve this thing. There will be maybe encroachments issue, and maybe different countries have different level of resources to monitor all these things. But I think every country is the forest department trying their best to better protect the forest for us and also for future generations.
Okay, thank you for your explanation, Wilson, because this is the international issues, right?
Yeah.
About deforestation, forest degradations, climate change, yeah. Everything. Everyone in the universe just discuss about the forest, tropical forest deforestation and like this. Okay, I think now we arrive at the end of the course. So if you have any questions about anything we discussed today, please feel free to send email to the organizing committee. We will forward your question to Dr. Wilson and send the answer back to you as soon as possible. So now we arrive to the end of the course. Before closing the online course, I would like to take a short conclusion for what the speaker presented today. To capture and analyze more information of a forest landscape, we can use remote sensing technology with many options of satellite image resolutions, depending on your purpose. I think that's all short conclusions. And for the last, I think the organizing committee have made a digital certificate as the thankfulness to Dr. Wilson for his valuable knowledge sharing today. Okay, this is the digital certificate for Dr. Wilson on behalf of the Forestry Faculty of Mulawarman University and the organizing committee of the online summer course. I would like to thank Dr. Wilson for an amazing inspiration in scientific work. So please be kind to receive this digital certificate.
Okay, thank you. Thank you very much.
This certificate, yeah.
This certificate.
Okay, this certificate will also be sent to your email soon, Dr. Wilson. So, ladies and gentlemen, please give applause to our speaker today. So I also greatly appreciate all participants for their active participation in the current course. We hope you can learn something today. I also would like to apologize if I made many mistakes as moderator during these sessions. Thank you very much and see you in the other session of the Mulawarman summer course. I'm Kiswanto. Assalamualaikum warahmatullahi wabarakatuh. Good morning and have a good day.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Wilson.
Oke, makasih. Sampai ketemu hari Senin, Bapak Ibu, nggih. Makasih.
Nggih, Bu.
Recording stopped.